Hi, in this video, we want to look at a little bit of set theory for business analytics. Okay, so set theory, it really is like the foundation. When I say foundation, I mean like the deepest aspect of the foundation of statistics. So statistics is, a branch of mathematics, and it's basically how we model what's going on is that we take probability. And so what we do, we assume that the data that we are observing comes from probabilistic structures in mathematics. And that's where we get our foundation for that. Well, the foundation of probability is going to be measure theory, and the foundation of measure theory is set theory. Okay, so now all that stuff, all that set theory, measure theory, we're not going to need, and we're only going to need a little bit of probability for business analytics. So we're just going to touch on this stuff. We're not going to go deep. We're just going to take a look at it just so that we have a feel for what's going on as we work through these problems, as we try to understand what's going on. Now, some things I'm going to say are not 100% mathematically rigorous, but that's okay for our purposes here. If you are, a math major, if you are a statistics major, you're going to have a more complete definition of some of these items. You're right. Those are the correct way to go. But for our purposes here, we don't need to go that deep, and we're not going to. All right, so the first thing we need to talk about are sets. What are sets? Well, a set is a collection of items. All right, that sounds so vague. That sounds so general. All right, so before we could even start talking about measurements, right? We had to have the idea of a number before we could, we could talk about height, 5'10", 5'11", 4 foot tall, 6 feet tall, stuff like that. We have to have a number. We have to have a number like that. And so, before I even started talking about measuring things, I had to talk about 1, 2, 3, 4, and so on. All right, so sets are kind of going way back to the most basic idea here, where a set mathematically, it's just a collection of objects. Now, this collection could be really anything that, for the purpose of business statistics, that we could think of. Now, there are some things in higher mathematics that sets cannot hold. We're not going to worry about that. We're just going to worry about the overall general idea is that a set is a collection of items. For example, I could have the set of cars in Orlando. I could have the set of NBA players. I could have the set of trees in North America. Now, these are all objects. These are a collection of items. And a set is just all of them together in one group mathematically. Okay, so we are talking about math, so I want to get into mathematical operations. I want to talk about mathematical relationships after this. So before I can do that, we need to say that a set is a collection of distinct items. All right, so, and we call those items elements. All right, so distinct just means if I have any two, I can tell if they're the same or different. Okay, so we're not in any ambiguity going on. Anytime I take two items, I know if they're the same or not. Now, when I talk about sets, I'm not talking about, I don't know about the number of items. We don't care about that. We just care about what items are in that collection. So if I was to have, the set of, red Mustangs, and I had the same Mustang multiple times, that's fine. We don't really care about the number of items because that is a different mathematical structure. We just care about, is it in there or is it not? That's it. And telling the difference between two things. All right, so now a subset is a sub-collection. All right, so given any two sets, A and B, A is a subset of B if every element of A is also an element of B. Okay, so what this is a mathematical way of saying if everything in A is inside B, then A is a subset of B. Now, something about this, if you pay really close attention to this definition, you'll realize that a set is always a subset of itself. Okay, now it does seem weird, that seems odd. Why would you do this? Well, mathematically, this works out very nicely for a lot of things that are going on. So if you go into higher mathematics, you'll see that we really need to have items being their own subset to make a easier to work with theoretical structure. Now, if there is something in B that is not in A, and everything in A is in B, then A is called a proper subset. Oh, and this is a typo. That should be an A. That should be an A. Oh my gosh, I'm so embarrassed. All right, so if A is a subset of B, and there is something in B not in A, then A is a proper subset. All right, now the sample space. All right, so the sample space is the collection of all possible events that we're interested in. Okay, so if we're talking about people in the United States, every single, and I'm sampling, I want to do statistics, trying to get an understanding of people in the United States, every single person in the United States is part of that sample space. All right, so now the event space. The event space is a set of events that result in a particular outcome. Okay, sounds kind of weird. So think about this. Think about the outcome of interest being a red car. Okay, then the event space would contain all the red Mustangs, all the red Camaros, all the red Challengers, and so on. And I like muscle cars. I like American muscle cars. So I'm going to list those out. So each individual red car together gives me the event space of a red car. So, you know, a red F-150 would count for this purpose. So the event space is just saying, hey, this is the collection of items that results in what I'm concerned with. So if I'm concerned with like a red car, I don't care that it's a red Mustang. I care that it's a red car. Just it being a Mustang is just a more specific feature about it. All right, now the elementary space is the smallest, simplest representation of the items we have on there. Okay, so here, if I was interested in cars, individual cars would be my elementary space. It's the smallest possible sampling event possible that results in what I'm interested in. Usually in business statistics, this is not an issue. Where this comes up in statistics is where I know that like what I'm interested in is contained inside a set, but I don't know where inside. So for example, if I was to have, you know, like if I was to know that someone in a room was sick, but I did not know who it was in that room, from that point of view, the elementary space is that entire room because I can't narrow it down. It's like, where is the person that's sick? So actually, let me reword this. Think about classrooms, and I have students throughout an entire school in different classrooms, and I know somebody is sick in. I know when a room has a sick student, but I don't know which student is sick. And there, the elementary space is the entire classroom because that is the most refined knowledge I have, most refined representation I have for the situation. All right, now the complement is the set of everything in the sample space that's not in the set under consideration. So the complement of A is everything that's not in A, but in the sample space, which is a very complicated thing to say. So the complement of A is everything in the sample space that is not in A. All right, now, okay, so now I've avoided using mathematical notation because I want this to be more colloquial, more accessible, but at this point, I gotta do it. There's nothing that I can do. All right, this funny looking E thing says inside. That's what it says. So X is an element, and this is S. All right, so this part here, this is saying all elements in the sample space. Now, this bar says given. This is given the next piece of information. Now here, this funny looking E thing with a slash through says not inside. All right, so this is saying X that is not inside A. So this is everything in the sample space given that it is not in A. That's the complement of the set A. And one way to denote this is the set with a bar on top. Another way is to put a C in the subscript. This, yeah, something like that. Either way, we'll know what you're talking about. Now the union is the set of elements that's in one or the other or both. This is inclusive or. So here, this A union B, so you can call this a cup, by the way. This U, funny looking U thing, it's not U, it's a union. And if you want to, you can call it cup. A union B is everything in the sample space such that it's in A, or it's in B, or it's in both. This is inclusive or. Now the intersection has this weird thing in here, and you can call this cap if you want. A intersect B is everything in the sample space given that AX is in A and it's in B. So it has to be in both. It has to be in both A and B. Now disjoint events, mutually exclusive, this means that there's no overlap between them. There's nothing in common between the two sets. This is important in statistics because why we care about this is so that we can break apart the different possible events going on. Now the difference between two sets is the collection of items that's in the first one, but not the second one. All right, so A, difference B, so we use a subtraction symbol for this. So this is everything that's in A that is not in B. And this is equivalent to A minus the intersection between A and B. All right, so what's going on is that this is everything that's in A that's not in B. Okay. Now, commutative laws, A union B is equal to B union A. A intersect B is equal to B intersect A. All right, commutative means that we can switch the order freely. Just like when you're doing addition, you can switch the order of the numbers and it doesn't change the result. But like subtraction is not commutative. If I have 1 minus 2, that's different than 2 minus 1. I'll get a negative number if I start switching one way, and I'll get a positive number if I switch it the other. So commutative means I can change the order around the operation. So A union B, I can switch the order of the sets and I get the same thing. Intersection, A intersect B, if I switch the order, I get the same thing. Now the associative laws, what this says I can, if I'm doing the same operation every single time, all unions or all intersections, I can go about and I can change the order of parentheses however I want without changing results. So here, if I was to do B union C and then do a union between the result of A and the parenthesis, that's the same as doing A union B first, then doing a union. Now, if I'm doing intersection, if I was to go B intersect C, then take an intersection with A, that'll be the same thing if I instead I did A intersect B first, then took the result and intersect with C. So here, it doesn't matter which one associates with the other first, I can switch it up freely. Something that is very important about this is that you'll notice I have union, union both times here. I have union, union both times here. It has to be the same operation. That is very, very important. Here, intersect, intersect, same operation, intersect, intersect, same operation. Now we have a distributive laws, and this is similar to the distributive properties in algebra, that now here, you notice I have union, intersection. If I go A union, the intersection, that's the same as A union B, A union C, take the intersection between the two. Now if I do A intersect the union of B and C, this is the same as A intersect B, A intersect C, and then union of the two parentheses. So I can change the order so I can go freely about this to get things to be easier to work with. Now De Morgan's laws, the bar should be going across this whole thing, is that if I take the complement of A union B, this is equal to A. So if I do the complement of A union B, the whole thing, this is equal to the complement of A intersect the complement of B. You'll notice that when I take a complement, it's like the operation flips over. The union becomes an intersection. Here, the intersection becomes a union. Now, the next thing to talk about is a sure event. A sure event is one that has probability 1. All right, that's all I've got for you. Take care and goodbye.